Okay, good morning. So today I want to talk about the next part of the lesson in Math 5, and this is a very interesting, and they call it principle. Usually in mathematics, when we say that a statement is a principle, it means that we don't want to prove it. But of course, I will call it a theorem because in principle you can prove it. But this is so trivial that people call it the pigeonhole principle, and it is simple to state it. If you have, for example, 10 pigeons and then you have only 9 pigeonholes, and if they are supposed to go inside these pigeonholes, there is at least one pigeonhole that should contain more than 1 pigeons. Yes, so that's so trivial. This is why people call it the pigeonhole principle. You might think that, okay, so trivial statement, how this can help us to solve some math problems. Of course, let us be patient and see how this will work. Okay, so if I want to state it formally, this theorem is very famous. We call it the pigeonhole principle. And let me write this statement for you. If m pigeons occupy n pigeonholes and m, the number of pigeons, is greater than n, the number of pigeonholes, then at least one pigeonhole contains more than one pigeon. Yes? Of course, let me just, even though this seems very trivial, but assume that you really want to give a rigorous proof for this. So let us see how we can do that. Okay, proof. So I would say that let n sub k, where k between 1 and n, the number of pigeonholes, is a natural number, denotes the number of pigeons in the kth pigeonhole. After the pigeons are distributed in the pigeonholes. What we want to show that there exists, yes, a k such that n of k is greater than 2, greater than or equal to 2. We want to show that at least there is a pigeonhole which contains greater than or equal to 2 pigeons. And we prove it by contradiction. Assume that this is not the case. And okay, now can you tell me what happens if this is not the case? Assume that this is not the case, and what?
That there is only one pigeon in every pigeonhole.
No. The correct statement. The people who have actually math specialization should be able to answer it quickly. But of course, this is a mathematical logic, so it doesn't need that you have that course before. But what is the negation of this statement? I want to say that there exists at least one pigeonhole containing 2 or more pigeons.
All pigeons' holes have less than 2 pigeons.
Yes. So and all pigeonholes. So this is the existential quantifier, the people who had math specialization, and the negation of this is and all pigeonholes contain less than 2 pigeons. Is that clear? I want to show that there is at least one pigeonhole containing at least 2 pigeons. If this is not the case, it means that all pigeonholes contain less than 2 pigeons. Yes, and therefore, what happens? If I add n1 plus n2 plus n3, and if I add them up to n sub n, this means that the number of pigeons in the first pigeonhole, this means that the number of pigeons in the second pigeonhole, this means that the number of pigeons in the third one, and this means that the number of pigeons in the last pigeonhole, and that is the nth pigeonhole, yes? On the one hand, what is the answer to this sum? Can you tell me? If I add them up, all the number of pigeons in each one of these pigeonholes, what should I get at the end?
M.
I should get n. Yes, m. Sorry, I should get m because the total number of pigeonholes is the total number of pigeons is assumed to be m. And now I am adding the number of pigeons in the first one plus the number of pigeons in the second one up to the number of pigeons in the last one. So it is clear that this sum is equal to m, even though I don't know what are the values for these individual pigeonholes. But I know that the sum should be equal to m. But now, based on this assumption, all pigeonholes contain less than 2. Yes, so less than 2 means what? So it means that less than 2 means less than or equal to 1. Yes, because the number of pigeons is a natural number. So when you say that this is less than 2, it means that this is less than or equal to 1. Yes, okay. If that is the case, then this means that this sum, on the other hand, is smaller than 1 plus 1 plus 1 up to plus 1. Yes, because I am assuming that all pigeonholes contain less than 2 pigeons. It means that all pigeonholes contain at least 1. Yes, at most 1. Or it means that this is less than or equal to 1. But then how many ones do you see here? I have n ones, yes? And then this becomes equal to n. Okay, but this is contradiction. So therefore, m, which is equal to this sum, is less than or equal to this sum, which is equal to n. So this means that m is less than or equal to n, yes? So therefore, m is less than or equal to m, which contradicts the assumption m is greater than n. Okay, so this means that this is of course very, very simple, and I don't think your book has written the proof, but if you really want to see this is a theorem, not a principle, this is the reason that this is correct. But intuitively, it is so clear that we call it principle. If I have, for example, 15 marbles, and if I have only 14 boxes, and I want to distribute these marbles into these boxes, it is completely clear that there is at least one box containing more than one marble. Yes, it's so trivial. Any questions so far? Okay. So let us solve some examples now. Example number 1. Show that in any group consisting of 13 people, there are at least 2 people that have their birthday during the same month. Okay, so that is exactly the pigeonhole principle one, but when you state it in this one, it becomes a little bit more exciting. So for example, I don't know how many students are now in our class. So I think so. I saw the last one was nearly 20. So it's completely clear for me that there are at least 2 of you have the same your birthdays in the same month. So I really don't need to know. I don't need any extra information to be able to conclude that. But even 13 people was enough to make me sure that this is the case. Okay, so let me see. So let me read the question again. Show that in any group consisting of 13 people, I don't need any extra information. As soon as I have 13 people in a group, then I can immediately assert that there are at least 2 people in this group that they have their birthday during the same month. So if you want to write this, how we can write this? So if you want to answer this in an exam, so you need to somehow show that you are using the pigeonhole principle. So it means that you need to give the role of pigeons to some part of this problem and give the role of the pigeonholes into another thing, okay? And then say that, okay, the number of pigeons is more than the number of pigeonholes. So according to the pigeonhole principle, there should be one pigeonhole, at least one pigeonhole containing more than one pigeon. Yes. Okay, now can you tell me what will play the role of pigeonholes in this problem?
The number of months in 1 year.
Yeah, exactly. So I would say, for example, I can consider this situation. For example, I will have a box or whatever, I call it January. Yes. And then I will have another box. So I can call it February. February, yes. And then we can continue until the last month. And I can write on it December, yes. So, but I know that how many months or how many pigeonholes are there? There are 12 of them. And then it means that I start calling them. I don't need any information. Okay, for example, if the first one is born in January, I will put that person in this box. If that person is born in February, I will put that person in this box, and etc. So when I call the first person, it is in one of them. Yes. If I call the second person, it is still in one of them. Okay. If I had only 12 people available, there is no guarantee for this, even though it might happen. Yes. Even if I have 2 people, it might happen that both of them are being born in January. So it is possible even for 2 people to have this situation. But the point is that there is no guarantee for that. We need extra information. But if I don't have extra information, so you see, it is clear that 12 people might not work. Yes, because if I have a group of 12 people, if I am very unlucky, it might happen that the first person is born in January, the second person is born in February, and finally the last person is born in December. And there is no guarantee that at least 2 of them are born in the same month. But as soon as I have 13 people available, then I can definitely claim that this is true. So this is what I want you to understand about the pigeonhole principle. Yes, because now 13 people, we have 13 pigeons and only 12 pigeonholes, and I want to distribute these pigeons inside these pigeonholes. Then according to the pigeonhole principle, there exists at least one pigeonhole containing at least 2 pigeons. It means that there are at least 2 people that are born in the same month. Yes, so I would say that if so, since 13 is greater than 12, according to the pigeonhole principle, there is at least one pigeonhole containing at least 2 pigeons. Yes, is that clear? So this is the same statement, but stating it in this way is a little bit more exciting, yes? Even though it was very trivial, when you think it is really trivial. Any questions? Okay, so now let us go to the next one. Okay, how do you answer this question? At least how many times a die should be rolled so that getting 2 same results is guaranteed? What if getting 3 same results is supposed to be guaranteed? You have a just normal die with 6 faces, 1 up to 6. You are answering the first one, yes?
Yep.
At least how many times a die should be rolled so that getting 2 same results is guaranteed? Yes, it should be 7. Is that clear for everyone? Because if I just roll it 6 times, it might happen that the first time I get 1, the second time I get 2, and the 6th time I get 6. None of them are the same. But as soon as I roll it 7 times, it is inevitable. Is that understandable? So I don't want to spend so much time. If we have extra time, you can work on yourself on the problems. But let me just write 7. So I think it's clear, yes? So the answer to the first part is 7. What if 3 same results is supposed to be guaranteed? Then what do you think?
It should be 13.
No. By 13 times, it is not guaranteed. It might happen, of course. Yes. So it might happen only 3 times is enough. Yes. I roll the dice. I roll the die first. It becomes 1, and then I roll it again. It coincidentally becomes 1 again, and then I roll it again. It becomes 1. So it means that it is possible to achieve this goal only by 3 times, but it is not 100% guaranteed that by 3 times I can get to this. I want to make sure before I start doing it, I want to say that, okay, if I do it this number of times, it is guaranteed that I will have 3 of them the same. What is that number at least? Yes, yeah, I'm really sorry. Yes, you are right. That was 13. Yes, thank you very much. I was confused. I don't know, for some reason I was taking it with something else. Yes, you said 13, and that is correct. Yes, because you say that, okay, if I roll it 6 times, if I am very unlucky, I might get from 1 to 6. And if I roll it 6 more times, if I am again unlucky, I might get from 1 to 6 again. So by 12 times, it is not still guaranteed, because then I will have 2 same results for each one of those numbers. The same results for each one of those numbers. But then I need to roll it once more. As soon as I roll it once more, it is guaranteed that I have at least a result which is repeated 3 times. Is that clear? Sorry for that. Okay. Now let us make it a little bit more interesting. So example number 3, 12 positive integers are randomly chosen. So from the set of natural numbers, you just randomly choose 12 positive integers. Show that among these numbers, there are 2 integers that have the same remainder in division by 8. Okay? Is it possible that there are 3 integers among these numbers having the same remainder when divided by 8? When divided by 8, is the existence of such 3 numbers guaranteed? At least how many positive integers one should one choose so that the existence of at least 3 integers with the same remainder in division by 8 is guaranteed if one chooses the numbers randomly. Okay, I will pause the video and I want you try to convince yourself about the parts of this question, and I will come back and we solve it together. Okay. Okay, so any answers? So first of all, tell me, do you see that this is not that trivial? Yes. Yeah, so I am stating a problem, especially the first part. I have 12 positive integers that are chosen randomly. They can be small numbers, they can be very big numbers, we don't know. I just know that I have 12 positive integers in my hand. But I am completely sure, I want to show that I am completely sure that among these numbers that I have in my hand, there are at least 2 integers having the same remainder in division by 8. So it means that I take these numbers one by one and I divide them by 8 and I find the remainder. At the end, I will definitely see that at least there are 2 numbers having the same remainder when I divide them by 8. So you see, it is exactly the same scenario, but it's expressed in a way that is not that trivial as the pigeonhole principle itself. So my recommendation here is that you need to try to find what you want to give, what you want to assume to be pigeons and what you want to assume to be pigeonholes. So you need to find the role for the pigeon and pigeonholes according to the problem in hand. And I have intentionally actually used 12 here. I will talk about that later. But let me ask you first, do you have any idea how we can reason for the first part?
We can say that if x is an integer, then there are 8 different possible outcomes if we divide it by 8.
As the remainder, yes.
Yes.
Yes, exactly.
And that would be 0, 1, 2, 3, 4, 5, 6, and 7.
Yes.
Which is in total 8 different outcomes. And if we say that the number of outcomes is the pigeonholes and the 12 positive integers are the pigeons.
Exactly.
And
thank you. Yeah, exactly. Thank you. So that is the whole point. Hopefully everybody understood, yes? So from what we learned before, from part A, so in part A, we learned in number theory that if you divide a number by 8, so let n be a positive integer. Yes, then we learned in number theory that n can be written as 8 times q plus r. Here, if you remember, q is called the quotient and r is called the remainder, but we know that r is a number in the set of integers where r is between 0 greater than or equal to 0 and is smaller than 8, if you remember. So it means that, therefore, R can be 0, 1, 2, 3, 4, 5, 6, and 7. And then how many of them are there? There are 8 numbers, yes? So it means that if you want to give the role if you want to know what is the role of pigeons and pigeonholes, you can say that, okay, I take a box and write 0 on it. What does this mean? It means that when I divide a number that I have chosen by 8, and if its remainder is 0, I will take that number and put it inside this box. I will have another box. I will write 1 inside it. So this means that if I divide my number and it's the remainder, if the remainder is 1, I will take that number and put it inside this box. But because of this rule that we learned in number theory, I know that I have only 8 boxes available for the remainders of the division of a number by 8. And those are 0, 1, up to the last one is 7. Okay, so if I ask you how many boxes or how many pigeonholes I have, I would say that I have 8 pigeonholes. And then how many pigeons I have, I can give the roll of pigeons to the numbers that I have chosen. I have 12 of them, okay? But I know that 12 is greater than 8. So therefore, according to pigeonhole principle, so let me write P. According to pigeonhole principle, there is at least one pigeonhole that contains more than one pigeon. Okay, so it means that there are at least 2 numbers in one of these boxes. Okay, by the way, I exaggerated a little bit. Do I really need to choose 12 random numbers, or I can choose less than 12 but still make sure that there are at least 2 integers having the same remainder when I divide them by 8? What is the minimum value that I can write in the question so that still this result is guaranteed?
9.
Yeah, that's 9. Because I just need to have more pigeons than pigeonholes, yes? Because the number of pigeonholes is 8, if I choose 9 integers, that is still possible to draw the same conclusion, okay? But I wrote it 12 because I just want to show that 12 is also working, okay? Any questions? Everyone understands what's going on? Okay, let us go to the next question. Is it possible that there are 3 integers among these numbers having the same remainder when divided by 8? Is it possible? Yes or no?
It's possible, but it's not guaranteed.
Exactly. Okay, exactly. So it is possible. The answer to the first part is yes, it's possible. Is the existence of such 3 numbers guaranteed? The answer is no. If you understand, let me not explain it more. Do you understand, everyone? Okay. At least how many positive integers one should choose so that the existence of at least 3 integers with the same remainder in division by 8 is guaranteed if one chooses the numbers randomly?
17, right?
What?
17.
17. Yes. So because you say that the number of pigeonholes is 8, so I multiplied by 2. it is 16, but 16 is not enough, because if I'm so unlucky, the first 8 will fill from the first box to the last box, and the second set of 6 integers will fill from the first one again to the last one. So you see that if I choose 16, it is not still guaranteed, but as soon as I choose 17, then it is definitely guaranteed that at least 3 of them have the same remainder if I divide them by 8. Yes. So let me just write these things. So for part B, I would say yes. And the second answer is no. For this next one, the answer is 70. Okay, now hopefully you understand what's going on in this pigeonhole principle stuff. Okay, now let us look at this problem. Show that if 51 elements of this set, the set contains all natural numbers 1, 2, 3 up to 100. Show that if 51 elements of the set are chosen, even randomly. So usually these words I am emphasizing in the setup of these kind of problems, you do not see these words, okay? Are chosen even randomly, then there are at least 2 numbers among the chosen ones, so that their sum is 101. Is the same result still guaranteed if we choose only 15 elements of this set? Okay, I will pause the video and let you think about it a little bit. Yes. Okay. Could you solve the problem? Could you come to an argument for this?
Well, if we divide the numbers in the set into pairs whose
Exactly.
sums make up 101. So
Okay,
like
can you tell me what are those? So we say that consider the following subsets of A, yes? So what can you tell me one of them?
1 and 100.
1 and 100. The other one is, for example, 2 and what? 99. Yes. And if I continue this list, it will go up to what?
49 and 52, and finally 50 and 51.
Yes, exactly. Thank you. Yes, that is a good strategy. So if you consider these sets, all of them are subsets of these sets. First of all, how many subsets you see in my list here?
50.
50. Why? Because you see the first one is 1, the second one is 2, the next one is 3, 49, 50. So it's clear that I have 50, I have 50 pigeonholes. But I am choosing 51 numbers. Okay, first of all, you see that if you consider these subsets, it contains all these elements, yes? 1, 2, up to 50, and then 51, 52, up to 99, 100. So I am considering all the elements of my set when I consider them as these subsets, each containing 2 elements. So now, if I, for example, now I start choosing a number in random. For example, any number that I choose belongs to one of these pairs, not more. Yes, it is clear. If the number is 1, of course, this number belongs here. If the number is 52, the number belongs here. Yes. So if I just choose 50 numbers, it is clear that this is not enough. Might be the first one is 1. If I choose 50 numbers randomly, it might happen It's not very likely, but it might happen that the first one is 1, the second one is 2, the next, the 49th one is 49, and the last one is 50. So I have 50 numbers in my list. The sum of none of them is equal to 101. Yes, but as soon as I choose 51 elements, then it means that because I have only 50 pigeonholes, then it means that 2 of my numbers should belong to the same pigeonhole. If those numbers belong here, it means that one of them is 2, the other one is 99, and I achieved my goal because the sum is 101. If the numbers are these two, then definitely the sum is again 101. Yes? I don't want to write it to spend time on it, but I hope that this is clear, the understanding. But you see that this problem is not trivial at all in the beginning. If you don't have any plan, like this, for example, to convince yourself of everyone that this is indeed the case, might be it is not completely clear why this is the case. Any questions here? Do you understand what's going on? And by the way, there are problems that are extremely hard to design these schemes, so to design this way of argument so that you can use the pigeonhole principle. But of course, these are not at the level of your book. So I will give you some more interesting ones, but I would consider this one also an interesting one. It was not trivial at all in the beginning. Is there any questions here? Okay, let us see what is the next problem. 13 positive integers are randomly chosen. Show that there are 2 integers among these numbers whose difference is divisible by 12. You see, these are really nice mathematical statements which are not trivial at all, but we are going to use this very trivial principle of pigeonhole principle to be able to guarantee these results. So I am telling you that you just choose 13 natural numbers randomly. It is always guaranteed that in your list, you can find at least 2 numbers, so that when you subtract those numbers and then divide the results by 12, the remainder is 0. I want you to understand this is a very big claim. Yes, it seems that I have a lot of degrees of freedom. In principle, I have infinitely many degrees of freedom. Yes, because I have an infinitely big set in front of me, the set of natural numbers, and I want to choose 13 positive integers from this infinitely big list. It means that I have infinitely many degrees of freedom in front of me. But still, I can guarantee that in my list of 13 positive integers, there are at least 2 numbers, so that the difference is divisible by 12. So that's, I would say that I want you to feel it. It's a really big claim. Because the reason that this problem seems a little bit hard, because I have infinitely many degrees of freedom available, but still I can say something very concrete about this set of 13 positive integers. This is the way that I want you to feel the power of this very, very innocent, simple principle of pigeonhole principle. Okay? Okay, I will pause the video and then I will let you to think about it. Okay? Okay, do you have any plan for this problem?
We can use the divisibility way
Yes.
again.
How?
Then, well, we're dividing the difference between 2 integers, so that their difference is another integer.
Yes.
Which means that that integer, there are 12 different possible outcomes if it is divided by 12.
Let me think in this way. Let me think a little bit. So if I have 13 positive integers, what you are saying, you are talking about differences, but there are more than 13 differences, yes? This is not going to work, even though your idea is correct, but you need to change it a little bit. Do you understand what I mean? Because if I have 13 positive integers in my hand, I want to consider the difference. I want to show that there is at least a pair, so that the difference of that pair is divisible by 12. But then how many pairs I have? It's more than this number, yes? You understand what I mean?
Yes.
Yeah, so that is not exact, but the idea is clear. So what I'm saying is that if you have number 1, number 2, number 13, I have 13 numbers in my list. The way that you want to argue, you are arguing directly about the differences. But I have much more. If you study, and we will later study, if we will have 13 times 6 pairs. So it is 78 pairs. So if you want to consider the differences of all these numbers 2 by 2, then you will consider 78. As you will consider 78 pairs. That was not the way that I was thinking. Is it correct or not? So you are saying that I have 2 numbers, the difference is an integer, yes, and I divide that integer. No, this is not working, I think, because then it doesn't matter how many numbers you have. Yeah, you need to have, okay. So let me move on the safe side, yes? Can you change the argument a little bit? Or any other one? Anyone else? Okay, I would say it in this way. I will think about your argument, by the way, as well. I am a little bit confused myself, but I was thinking that because I have 13 positive integers, so if I divide a number, I would say let n be a natural number. So we know that n is so let me write it in this way. Sorry. We know that the remainder of the division of any natural number by 12 is one of the following numbers. So let me give this again. 0 here, the next number might be 1, the next number is 2, the next number is 2, and then I continue. What is the last possibility when I divide the number by 12? the remainders that I might get are 0, 1, 2, up to 11, yes? And if I ask you how many possibility I have, you would say 12 pigeonholes, yes? Okay, but I have told you that you choose 13 numbers. So then I would say that since 13 is greater than 12, according to pigeonhole principle, there are at least 2 integers, say n1 and n2, in my list of chosen numbers such that they have the same remainder when divided by 12. So I just want to wait. Is this argument clear for everyone? So I said that we know from number theory that if I have just any number, any natural number, and I divide it by 12, the possible remainders are 0, 1, 2, up to 11. And if I ask you how many possibilities do I have, you would say 12. Yes, but I have chosen 13 numbers. So this is definitely guaranteed by the principle of pigeonhole principle that at least 2 integers from my list have the same remainder when I divide those numbers by 12. That is what I have written so far. Is that clear for everyone? Okay, I called one of them N1 and the other one N2. So what does it mean? N1, when I divide it by 12, it gives me a quotient, let me call it Q1, and it gives me a remainder, I will call it R. But if I ask you what that R is, you cannot definitely answer, but you will say that it is one of these things in my list. And then N2 is what? Is 12Q2, but the remainder is the same, yes? Because there are at least 2 integers, say N1 and N2, so that the remainders by 12 are the same. So this is why I do not write R1 and R2, because N1 and N2 by this argument have the same remainder when I divide them by 12. Now I want to talk about the difference. So if I calculate the difference between these two, then it becomes 12Q1 plus R minus 12Q2 plus R. But then if I open the pair of brackets, positive R and negative R are canceled, and I will have 12 in common, so I can factor 12 out. It becomes Q1 minus Q2. Okay, so what does this mean? This means that the difference is a multiple of 12. When you say that the difference is a multiple of 12, so it means that the difference is divisible by 12. Okay, so this implies that 12, let me write it here, this implies that 12 divides this difference. And that's exactly what we wanted to show. We wanted to show that there is a pair of integers in my list so that the difference is divisible by 12. So yes, hopefully you agree with this argument. But the way that you wanted to mention it was to talk about the difference from the beginning. Is that also working or not? Is it working? You're saying that, okay, I have 13. Okay, I can think a little bit about that. Let me go to is there any question here for the way that I argued here? Is that clear for everyone?
Yes.
Okay, so let us go to the next problem. I also can think a little bit about the way that you have actually wanted to argue. So example number 6. This is also interesting. Each point of a plane is colored red or blue. randomly. Okay, so you have a plane. Plane means infinitely big plane. Yes, it actually divides the universe into two parts, upper part and lower part, if you can consider it in your brain horizontally. Okay, so when I say a plane, it means that it is infinitely large and it contains, of course, infinitely many points. And then I start randomly coloring the points red or blue. Okay, so each point of the plane is either red or blue. Show that it doesn't matter how I do it, still I have infinitely many degrees of freedom. Show that there are 2 points of the same color at distance 1 meter from each other. So I want you to feel that this is seems a very hard problem, but if you think a little bit closer about this, then you will find a way to use this very trivial pigeonhole principle to argue so that everyone are convinced that this is true. So the problem is that I have a plane containing infinitely many points, of course. I start coloring each point randomly, either red or blue. I want to show that it doesn't matter how this random process is done. Definitely, there are at least 2 points with the same color being 1 meter from each other. Okay? So let me pause the video. You can think a little bit, I will come back. Okay, any ideas about how to solve this problem? Okay, at least I hope that you can see that this simple principle can also be very handy and very powerful sometimes. If I give you the solution is very simple actually.
Isn't it just that because the plane is infinite,
Yes.
there are infinite many points on it,
Yes.
which means there are, if you are picking 2 points and they are the same, if you want to pick points and at least 2 of them are the same color, and they are either red or blue, then you have to pick only 3 points to be guaranteed that 2 of them are the same color. And well, 3 is less than infinity, so it's a guarantee that you find them.
So I agree with one part of that. Okay, but why they want we want to show that they have equal the distance between 2 same colored points is 1 meter. This is making it a little bit harder. So you not only want to claim that, you are not claiming that there are 2 points of the same color, but we want to show that if you look closely, you definitely find at least 1 pair of points of the same color, so that if I measure the distance between those 2 points, it is exactly 1 meter. So the way that you talked about the number of colors and points was correct. But how do you want to argue for the distance simultaneously as well?
Well, shouldn't it also be on a similar basis, because there are an infinite number of points?
Yes.
And which means there are an infinite number of pairs of points.
Yes.
Which means it's guaranteed that there is at least 1 pair of points with the distance of 1 meter.
No. Do you feel this? How do you feel that this is guaranteed? Because you say that, okay, the number of, I don't know, the number of points are infinite. So how do you come to this conclusion that this is guaranteed, that there are 2 points with the same color which have exactly 1 meter, which are exactly 1 meter away from each other? So I mean, even if you see the solution, then you would probably you would confess that this is the best way of actually saying this, so there would be no doubt about it. Any other one? Anyone else? Okay, so let me give you the argument. Okay, so that's a good problem, because at least you can feel that there is something going on here. Okay, so assume that, let me just try to do a plane. So here I have a plane. So assume that, of course, I cannot draw the real plane, but I'm just, so assume that this is your plane. It goes to infinity from all directions, up, down, and left and right. And then I am picking points. So I am just coloring them randomly. I don't know, for example, I color them, some of them blue. Yes, I color some of them red. Okay, this process is being done, but at the end of the day, of course, this process will never end because I have infinitely many possibilities, but you can imagine it, yes? Assume that this is done, and then what is happening? You have infinitely many points colored either blue or red. Okay, now I can give you a little bit of hint. Okay, consider an equilateral triangle with length equal to 1 meter. Does this help? So let me draw it with a different color. So assume that you have an equilateral triangle. Yeah, assume that this is an equilateral. All the sides are the same. So assume that this is your equilateral triangle, 1 meter, 1 meter, 1 meter. And then concentrate here. Can you understand what's going on now?
Yes.
Yes, can you just describe it?
The distance between the points is 1 meter, and because there are 3 points.
Yes.
It
So
means that
what is playing the role of pigeons in this problem? If you understand the reasoning, what is going to play the role of pigeons in this problem?
Is it the lines in between?
No. So these points, the corners, are going to play the role of the pigeons. And what is going to play the role of pigeonholes? Colors, red or blue. So let me just describe it for you. So you can imagine this situation in your head. I have a plane. I have some points colored in blue. Some points are colored in red in random. I don't know what is happening here. I know the situation, but I am telling you, take this triangle with you and just throw it here. Any way that you want to do it, okay? You take your triangle, your right angle triangle, and put it on your plane, okay? So what will happen? How many points you have here? You have 3 points. But these points are now the points on the plane as well. So one of them, each one of them is either red or blue. But at least 2 of them should be of the same color. Do you agree? Because I have 3 points, but I have only 2 colors. It is not possible I have different colors at different corners. 2 of them have to be the same color. Okay, say these 2 are blue. Okay, then exactly the distance between these 2 points is 1 meter. It might happen that these 2 are red. Okay, no problem. Still, I have 2 points with the same color red, which the distance between them is exactly equal to 1 meter. It might happen that these are different. It might happen these are different, but what I'm trying to say is that according to pigeonhole principle, it is not possible that all of them are different colors, because I have 3 points and I have only 2 colors. So at least 2 of them have to have the same color. And it doesn't matter which pair has the same color. The distance between those two is exactly 1 meter because of the construction of this equilateral triangle. Are you convinced now, 100% without any doubt, or not?
I am convinced.
Yeah, so you see, the argument is so simple. I hope that everyone is now convinced. It is very simple. I just consider a right angle, an equilateral triangle of length equal to 1 meter. And I say that, okay, if I take this triangle and put it on top of this plane, these points now will be points of the plane. And because all the points of the plane are colored in only 2 colors, red or blue, it means that this is also the same. So it means that if I put this triangle here, then of course I will get 3 points from the plane. 2 of them definitely have the same colors. And then those 2 have exactly distance equal to 1 meter. So then you realize that there is nothing particular about 1 meter. You can talk about 1 kilometer. You can talk about 0.5 meters and everything. It depends. I can just change the size of my equilateral triangle and follow the same argument. Is that understandable? So I think that this, now you understand, this statement is really, really powerful. Okay, before that you might say, okay, how can I guarantee that this is always the case? But hopefully by this very simple argument, you can immediately be convinced that this is always the case. Is it clear? Okay, there are some problems left. I would say that, okay, I will make it part 1. I will spend 1 more session on pigeonhole principles, solving a little bit harder problems. And then next week, I will go to combinatorics, which is also a very interesting and exciting topic in discrete mathematics. Any questions? Okay, so when I uploaded this, there are 2 more problems left. And we're supposed, you can think about these problems yourself. These are nice problems as well, okay? And I will come back and solve these problems in the next session for you, and I add more problems. Thank you very much, and sorry for these 2 minutes extra. Bye-bye.